A Mercedes-Benz taxi in Greece just crossed 4.6 million kilometers on its original engine. That's the equivalent of driving to the moon and back 6 times. The car? A 1976 W123. And that's just the beginning of what makes this machine unlike anything else ever built. Most people think they know the W123, but what you're about to discover will change how you see engineering forever. Secret number 10, the design that defied time. The W123 wasn't designed to look good for a year or even a decade. It was engineered to remain visually relevant for generations. Under the leadership of Bruno Sacco, Mercedes-Benz's chief stylist, the design team rejected every short-lived trend of the 1970s. No swooping curves, no exaggerated fins, no decorative chrome that served no purpose. Instead, Sacco applied what he called proportional harmony. Every line, every curve, every panel gap was calculated with geometric precision. The wide stance and upright grille projected authority. The precisely measured overhangs communicated balance. Even the headlamp cluster placement followed mathematical ratios designed to make the car appear planted and purposeful. But here's what most people miss. Sacco's team spent months in wind tunnels, testing every surface for aerodynamic efficiency. This wasn't about speed, it was about reducing wind noise and improving stability at highway cruising speeds. The beltline trim, the subtle body contours, even the angle of the rear window were all refined to let air flow smoothly over the car. The result? A design so timeless that 40 years later, the W123 still looks modern parked next to contemporary sedans. Sacco's philosophy became the foundation for Mercedes-Benz design language well into the 1990s, influencing every model that followed. Secret number 9, the OM617 engine built for immortality. The 5-cylinder OM617 diesel engine wasn't just powerful, it was deliberately over-engineered to outlast the car itself. Mercedes-Benz engineers built this engine knowing it would face decades of abuse in the hands of taxi drivers, delivery fleets, and drivers in countries with questionable fuel quality. The foundation was a cast iron block and head paired with a forged steel crankshaft. These weren't lightweight materials chosen for efficiency. They were heavy, dense, and capable of handling immense internal pressure without flexing or cracking. The connecting rods were oversized, thicker than necessary for the engine's output, creating structural redundancy that prevented catastrophic failure. Here's where it gets interesting. The OM617 used an indirect injection system, a technology most manufacturers abandoned for being inefficient. But Mercedes kept it because it delivered cleaner combustion and allowed smoother cold starts, critical for cars operating in extreme climates. A mechanical Bosch inline fuel pump metered fuel delivery with precision. No computers, no sensors, nothing that could fail in remote locations far from qualified technicians. The engine's oil capacity was massive, nearly 6 liters, with a deep sump design that kept oil circulating even during hard cornering or steep inclines. The cooling system was equally robust, maintaining stable temperatures during extended high-load operation. Dual fuel filters caught contaminants before they reached the injection system. And instead of rubber timing belts that degraded over time, Mercedes used gear-driven components that could run indefinitely. Taxi drivers in Athens discovered engines still running strong past 1 million kilometers. In Africa, W123s operated in desert heat with fuel quality that would destroy modern diesels within months. The OM617 didn't just survive, it thrived where other engines failed. Secret number 8, the suspension system, engineered for punishment. The W123 suspension wasn't designed for comfort alone. It was built to absorb years of punishment on the worst roads imaginable while maintaining precise handling that most modern cars can't match. At the front, Mercedes installed double wishbone suspension with coil springs and a stabilizer bar. This wasn't a cost-cutting measure like the McPherson struts used by competitors. Double wishbones provided exceptional control during hard braking and aggressive cornering, keeping the tires planted even when the road surface turned hostile. The rear used independent semi-trailing arms, meaning each wheel moved separately. When one wheel hit a pothole, the other side remained undisturbed. This kept the ride smooth on uneven terrain while preventing the body from pitching and rolling during lane changes. But the real genius was in the components themselves. Forged control arms instead of stamped steel, gas-filled shock absorbers that resisted fade during extended use, high-quality rubber bushings designed to last hundreds of thousands of kilometers without deterioration. Every piece was metal reinforced reinforced and tested beyond normal automotive standards. This created the signature magic carpet ride that made the W123 famous. The car absorbed bumps and rough pavement without transmitting harshness into the cabin, yet it responded to driver inputs with precision that felt connected to the road. Taxi drivers loading passengers and cargo day after day, navigating potholed streets in Berlin, cobblestones in Athens, and unpaved roads in rural Africa found that the suspension never quit. Decades later, many W123s still glide smoothly on their original suspension components, a testament to engineering that prioritized longevity over quarterly profits. Secret number 7, the vacuum-powered central locking system. In the 1970s, while other manufacturers were experimenting with unreliable electric motors for central locking, Mercedes-Benz engineered a system so ingenious it still works flawlessly in cars sitting unused for decades. The W123 used a vacuum-powered central locking system. No electric motors, no solenoids, just a network of air pressure lines, diaphragms, and vacuum pods connected throughout the car. When the driver turned the key in any door lock, a vacuum pump sent pressurized air through sealed lines, activating locks on all doors, the trunk, and even the fuel flap simultaneously. Completely silent, perfectly synchronized. Here's why this mattered. Electric systems of that era were plagued with failures. Water intrusion corroded contacts, motors burned out, wiring harnesses deteriorated. The vacuum system eliminated all these vulnerabilities. No electrical contacts meant no corrosion. No motors meant nothing to burn out. The system could hold vacuum pressure for weeks, meaning even if the car sat dormant, it functioned perfectly the moment you returned. This wasn't just innovation for the sake of technology. It was practical engineering solving real problems. Taxi drivers leaving their cars parked overnight in coastal cities with salt air found their locks still working years later. W123s in humid tropical climates avoided the electrical failures that plagued competitors. Even today, mechanics familiar with the W123 marvel at how many of these vacuum systems still operate with their original components. While modern cars suffer central locking failures requiring expensive electronic replacements, the W123's purely mechanical solution continues working as intended nearly 50 years later. Secret number 6, the global taxi phenomenon. The W123 didn't earn its legendary status in showrooms or auto magazines. It was forged in the toughest proving ground imaginable, the hands of taxi drivers who demanded absolute reliability because their livelihoods depended on it. From Berlin to Athens, Cairo to Khartoum, the W123 became the universal workhorse of professional drivers. These weren't garage-kept collector cars. They were machines subjected to relentless abuse. 18-hour shifts, stop-and-go traffic, long idling periods, overloaded trunks, passengers slamming doors thousands of times, roads that would break lesser vehicles within months. Taxi fleets discovered something remarkable. The W123 could cover hundreds of thousands of kilometers with nothing more than routine oil changes and basic maintenance. The OM617 diesel sipped fuel efficiently, making it economical to operate. Parts were standardized and interchangeable, meaning a mechanic in Athens could repair a car using components from Germany or Egypt. This created a global support network that kept W123s running in the most remote locations. In Greece, a taxi driver named Grigorios Sakyanidis drove his 1976 240D past 4.6 million kilometers. The original engine, the original transmission, minimal major repairs. When asked about the secret, he simply maintained it according to Mercedes specifications and never abused the machine beyond its considerable limits. It wasn't unusual to see W123 taxis still working after 30 or 40 years, often alongside their third or fourth generation of drivers. While competitors' vehicles were scrapped and replaced multiple times, the W123 persisted, proving that proper engineering could create a truly timeless machine. This real-world validation cemented the W123's reputation far more effectively than any marketing campaign ever could. Secret number 5, Arctic and tropical versions engineered for extremes. Most manufacturers build one car and hope it works everywhere. Mercedes-Benz took the opposite approach with the W123, creating specialized versions engineered specifically for the world's most hostile climates. The tropical models were designed for relentless heat, choking dust, and substandard fuel quality found in Middle Eastern and African markets. These cars received larger radiators with increased surface area for heat dissipation. Additional cooling fans provided extra airflow when temperatures climbed above 40 degrees Celsius. Ventilation systems were upgraded to handle desert dust without clogging. Even the fuel system was modified to tolerate the low-quality diesel common in developing nations. Meanwhile, the Arctic versions faced the opposite challenge: extreme cold that turned engine oil into sludge and froze moisture in fuel lines. These cars came equipped with powerful cabin heaters, double insulation throughout the body, and reinforced electrical systems designed for reliable cold starts and temperatures plunging below -30°C. Battery capacity was increased. Thicker oils were specified. Fuel lines received additional insulation to prevent diesel from gelling. But here's what separated Mercedes from competitors. These weren't superficial modifications. Engineers studied local conditions and target markets and adapted every relevant component. Carburetor tuning varied by region. Thermostat opening temperatures changed based on climate. Even paint formulations were adjusted to resist UV degradation in equatorial sun or road salt in Scandinavian winters. A W123 sold in Saudi Arabia was fundamentally different from one delivered to Norway, yet both were engineered to the same exacting standards. This obsessive attention to regional requirements meant the car performed optimally, whether traversing the Sahara Desert or navigating icy roads above the Arctic Circle. This level of specialization explains why W123s thrived in environments that destroyed other European sedans within years. Secret number 4, the parts interchangeability and global supply network. Mercedes-Benz did something remarkable with the W123 that modern manufacturers deliberately avoid. They engineered the car for effortless repair anywhere in the world. The parts interchangeability was extraordinary. Components from different model years often fit seamlessly. A suspension arm from a 1976 model could replace one on a 1984 car. Brake calipers, window regulators, door handles, even interior trim pieces shared dimensions and mounting points across the entire production run. This wasn't accidental. Mercedes intentionally minimized variations to simplify the supply chain and reduce the complexity mechanics faced when sourcing replacement parts. But the real genius was the global parts network Mercedes established. The company didn't just sell cars to developing nations and walk away. They set up authorized parts distributors in nearly every country where W123s operated. A taxi driver in Nairobi could order genuine Mercedes parts with the same ease as a mechanic in Stuttgart. This network ensured that even in remote locations, W123s could be maintained to factory specifications. The parts themselves were manufactured with the same obsessive quality standards as the cars. Replacement components weren't cheaper alternatives. They matched original equipment specifications exactly. Aftermarket suppliers eventually entered the market, but many mechanics preferred genuine Mercedes parts because they knew the quality was consistent and the fit was guaranteed. This created a self-sustaining ecosystem. As W123s aged, the extensive parts availability meant owners could economically maintain them rather than scrapping them for newer vehicles. Independent mechanics became experts in W123 repair, passing knowledge to apprentices who continued servicing these cars decades later. Online forums now connect enthusiasts worldwide, sharing part numbers, restoration techniques, and suppliers who still stock original components. Compare this to modern vehicles where parts compatibility changes every model year, forcing owners to source exact year components at premium prices. The W123's approach meant a car from 1976 and one from 1985 shared enough common parts that maintaining either remained straightforward 40 years later. This wasn't just convenient for owners, it was strategic brilliance. By making the W123 easy to repair and maintain globally, Mercedes ensured these cars stayed on the road longer, creating rolling advertisements for the brand's durability and cementing customer loyalty across generations. A mechanic who learned to service W123s in the 1980s became an advocate for Mercedes quality, influencing customers for decades. Secret number 3, the over-engineered cooling system. Mercedes-Benz engineers approached the W123's cooling system with a philosophy that seems foreign to modern automotive design. Build it with excess capacity so failure becomes virtually impossible. The radiator featured large surface area fins and thick copper cores designed for superior heat dissipation. This wasn't about handling normal driving conditions, it was engineered to maintain optimal temperature during the worst case scenarios, towing heavy loads up mountain passes, idling in traffic jams under desert sun, or sustained high-speed autobahn cruising for hours. A precision thermostat regulated coolant flow to maintain stable engine temperature regardless of external conditions. During cold starts, it restricted flow to help the engine reach operating temperature quickly. Under heavy load, it opened fully to maximize cooling capacity. This simple mechanical component eliminated the temperature fluctuations that caused premature wear in competitors' engines. The viscous fan clutch was particularly clever. It automatically adjusted fan speed based on heat levels detected through fluid viscosity changes. When cooling wasn't needed, the clutch reduced fan speed, minimizing parasitic drag on the engine and improving fuel efficiency. When temperatures rose, it locked up completely, maximizing airflow through the radiator. No sensors, no electronics, just pure mechanical intelligence. The water pump was cast metal, not the plastic components that fail in modern cars. It circulated coolant efficiently through reinforced hoses and corrosion-resistant passages designed to last indefinitely. In tropical and Middle Eastern versions, an auxiliary electric fan and even larger radiator provided additional insurance against overheating. The result, overheating, a common failure mode in 1970s and 1980s vehicles, was virtually eliminated in the W123. Taxi drivers in scorching climates ran these cars day after day without cooling system failures. The excess capacity meant the system operated well within its limits, dramatically extending component life. Secret number 2, the build quality and material selection. Walk up to a W123 and close the door. That solid thunk isn't an accident. It's the sound of engineering tolerances measured in fractions of millimeters and material chosen for longevity over cost savings. Mercedes-Benz specified thick gauge steel for the body panels, substantially heavier than competitors used. This added weight, yes, but it also added rigidity and durability. The steel was treated with multiple layers of corrosion protection, electro-galvanized coating, primer, base coat, and clear coat. In regions with harsh winters, additional undercoating protected the chassis from road salt that dissolved lesser vehicles within a decade. Panel gaps were obsessively controlled. Bruno Sacco's design team didn't just want the car to look good. They ensured consistent tolerances that improved weather sealing and prevented water intrusion. The rubber seals themselves were manufactured from high-quality compounds resistant to UV degradation and temperature extremes. Decades later, many W123s still have their original door seals functioning perfectly. Inside, the materials followed the same philosophy. The dashboard was constructed from thick, durable plastics and real wood trim, not the thin veneers competitors used. Switches and controls were made by Bosch and other premium suppliers, built to withstand hundreds of thousands of cycles without failure. The upholstery used tightly woven fabric or high-grade leather designed to resist wear from constant use. But it was the small details that revealed Mercedes' commitment. Wiring harnesses used thick insulation and proper routing to prevent chafing. Fasteners were rust-resistant alloys, not cheap steel that corroded. Even the paint quality exceeded industry standards, with multiple color coats creating depth and durability that kept W123s looking presentable decades after leaving the factory. This wasn't luxury for luxury's sake. It was purposeful material selection that ensured every component outlasted typical ownership cycles. When a taxi driver in Cairo kept his W123 running for 30 years, it wasn't luck. It was the inevitable result of choosing the right materials and manufacturing them to exacting standards. Secret number 1, the legacy that changed Mercedes-Benz forever. The W123's greatest secret isn't a component or engineering feature. It's what happened after production ended in 1985. This single model fundamentally altered how Mercedes-Benz viewed quality, durability, and brand identity for decades to come. Between 1975 and 1985, Mercedes produced 2.7 million W123s. But the story didn't end when the last car rolled off the assembly line. These machines kept running, kept accumulating miles, kept proving their worth long after competitors from the same era had been recycled into scrap metal. By the 1990s, automotive journalists began noticing something unusual. 20-year-old W123s were still common sights on roads worldwide, many still serving as taxis, many still wearing their original paint. This created an unexpected problem for Mercedes-Benz. Customers who experienced W123 reliability expected every subsequent model to match that standard. When newer models couldn't achieve the same longevity, complaints flooded in. The automotive press started questioning whether Mercedes had abandoned the engineering philosophy that made the W123 legendary. The company responded by making the W123's durability a cornerstone of their brand identity. Marketing campaigns featured aging W123s still in service. service. The phrase "built to last" became synonymous with Mercedes-Benz. Engineers on future models faced constant comparisons to the W123's benchmark for quality and longevity. Today, collector values reflect this legacy. Well-maintained W123s command premium prices, not as vintage curiosities, but as functional transportation that enthusiasts actually drive daily. Online communities share maintenance tips, source parts, and document million-kilometer examples. In some developing nations, W123s remain more valuable than newer cars because mechanics understand them and parts remain available. The W123 proves something controversial in modern automotive manufacturing. A car built to last generations is not only possible, but creates deeper customer loyalty and stronger brand equity than planned obsolescence ever could. It demonstrated that over-engineering, while expensive up front, pays dividends in reputation that compounds over decades.